For years, I've been fascinated with mechanisms that expand, that go from small to big. Many expanding mechanisms, like the Hoberman sphere and my extensors mechanisms, are based on scissor linkages. But sometime in the past couple of years, I realized that rack and pinion mechanisms can be used in place of those scissor linkages. So, hi, I'm Henry Segerman, and this is Expanding Racks. Let me tell you how these mechanisms work. This is the basic unit. Let's call it a double rack. It's got a rack on this side and another rack on the other side, and it also has a gear in the middle that can spin around. It gets a bit more interesting when you put two of them together, like this. They have rails that slide into grooves in each other, which hold the two double racks together, and their racks mesh into each other's gears, making the gears spin. Now let's add a third. Something new happens now. Since the outer red and orange racks both mesh with the gear on the middle green rack, when I pull the red rack away from the green, it rotates that gear, which then pushes the orange rack out. And the same thing when you go back in. And we can continue the chain with a fourth double rack. The pattern continues, and now when I move any two neighboring double racks together or apart, they all move together or apart at the same time. So we get an expanding and contracting stick with 1 degree of freedom. The last rack at the end of the stick doesn't really do anything because there's no gear for it to mesh with. So we can remove it like this. And yes, I didn't bother doing the red end, I only did the blue one. These racks are pretty short, but you can make the racks any length you want. Here's the same structure made from longer racks. It doesn't collapse down as short, but the overall expansion factor is better. This expanding racks design evolved from my recursive racks project. It also has a chain of parts, each with 2 racks that mesh into gears on the neighboring parts. We aren't zigzagging anymore with the new design, but otherwise the new mechanism works more or less the same as the old. There are, however, a couple of less obvious changes. First, in the old design, the racks could just come all the way out and the whole thing would fall apart. I stopped that happening in this version of the old design by adding these bolts on the ends of the racks. They hit the frame and stop the racks from coming out. But I found a more elegant solution for the expanding racks design. Here, the last gap between the teeth of the rack is filled in, so the rack cannot slide out past where a gear tooth is supposed to go into that missing gap. Second, in the old design, we step down a little bit each time you go from one part to the next in the chain. This is supposed to make sure that the racks are not in each other's way as the mechanism collapses down, but sometimes the order of the racks can get mixed up and the mechanism jams. The different levels also make it hard to see how we might be able to extend the pattern to make a full 2-dimensional grid rather than just a zigzag. So I wanted neighboring parts in the chain to be on the same level, not stepping up or down. This means that the racks have to point in the same direction rather than crossing each other, and they have to collect up to the side of each other. If 2 parts are in contact at any point of the motion, then they're in contact the whole time, with rails running along grooves in the other part. That means that there's no way for them to get out of position and crash into each other, avoiding the jamming problem with the previous design. Okay, so we can make a 1 degree of freedom extending stick. Next, let's see how to extend this to a 2-dimensional grid, starting by replacing this gear with a taller one. This taller version of the gear is going to allow it to interface with racks going above it in this direction. Next, we replace this little cap with a whole other double rack, like this. Okay, so there's not really anything going on just yet. All this blue stuff is just one rigid object. But what's going to happen is going to add more double racks to this upper layer, and one of those racks is going to mesh with the upper half of this taller gear, and that's going to transfer force from this lower stick to the upper stick. Okay, let's see it. As promised, when I move the lower rack, the motion gets transferred to the upper rack through that taller gear. So what's happening is that that taller gear is meshing with this rack on the orange part, and it's rotating in the blue part, and the upper half of that taller gear is meshing with this orange part here, and that's making the whole upper level move as well. When looking at the mechanism from this side, the lower double racks sort of shift to the left as you move along the stick. Green is to the left of red, orange is to the left of green, and so on. And that's also true for the upper racks. If I go this way, orange to the left of blue, green is to the left of orange, and it doesn't actually matter which way you look along the stick. If I'm going this way, green is to the left of red, orange to the left of green, and so on. But the lower racks have their teeth on the top, while the upper racks have their teeth on the bottom. So the upper and lower double racks actually mirror images of each other. If instead we have the same handedness on both layers like this, then one retracts while the other expands. I haven't played around with this much, but maybe there are some interesting things to do with it. Let me know in the comments if you have any ideas. Alright, so with opposite handedness on the 2 layers, we can take a bunch of parallel sticks and make a big grid that expands and contracts. That's all that's going on with the small big design and the high design from the start of the video. For the small big design, I used 2-color printing to put a thin layer of black on top of mostly white racks to outline the letters of the word small. When the grid expands, the letters get sheared apart, making them more or less unrecognizable, and instead we see the word big written in the double racks themselves. The high design is a bit wobbly. If I were to make it again, I would add more black racks in between the bits of the letters, like I did for the small big design. They add stability without affecting the readability of the word. This mechanism collapses down to here, which is actually not quite as small as if you just have a single stick and collapse that down as far as it goes. You can see the distance between these 2 bolts is a little bit less than the distance between these 2 bolts. You can also see there's a little gap here and here, which you don't get in just a single stick. And the reason that's happening is that you've got these very thick sticks, say the sticks for this L and this L here, that are crashing into each other around here, and that's stopping it from getting any smaller. And the reason that these sticks are so thick is that in the expanded version, you've got all of these double racks here that are spanning across the whole length of the design, and so you just need a lot of sticks here, and so those get in the way of each other as you collapse it down. So what happens if you want to make an even bigger grid with even thicker sticks? Does it collapse less and less? The answer is no, but how much you get to collapse depends on the length of the racks. Here's a full 6x6 grid made from relatively short racks that collapses down to here, where the end of this rack is about to crash into the end of this rack. And you see the same thing happening with these pairs of racks in this line across the mechanism. Now, suppose you wanted to make a bigger grid with more squares. Well, what would you do? You'd say, take a copy of this rack here and shift it down by this distance here between the bolts. And what would happen is that the end of the new rack would fit perfectly into this slot here, and that end would almost be crashing into the end of this rack. And so the whole thing tiles, and you could make this design with as many squares as you want, as big as you want, and would always be able to expand this far and collapse this far. The scale factor would always be the same. Now, suppose you wanted to make the racks themselves longer. That's another way to get better expansion factor. Well, if you just go out a little bit like this, you're not really gaining much. These two racks, if they were maybe a centimeter longer, they would be crashing into each other here, and you get a little bit extra size when it was expanded out like this, but you're losing exactly that same amount of expansion when it's collapsed down here. There is something interesting that happens when you get to around here, though. So now it looks like maybe you could expand them by maybe 2 centimeters, but actually you can go a lot further, because when they're this far apart, the line on the edge of this rack and the line on the edge of this rack are lining up, and in fact you could extend them past each other. You can't get into this amount of contraction anyway, so you can make your racks longer. There's a sort of dream for expanding mechanisms, where you'd somehow have a completely solid block of material when it's collapsed down. Then as the mechanism expands, every piece of material, the whole volume, will be efficiently used to make a strong expanded structure. And it feels like this mechanism is getting pretty close to that dream. As I was playing around with the lettering idea, making the high and the small big designs, I also wondered if it would be possible to have diagonal lines, since some letters are hard to draw with only horizontal and vertical lines. Here's the first thing I came up with. Obviously, it's a triangle. I wanted to make a shape with a loop in it because they tend to work better than just a branching tree shape. The forces can travel 2 ways around the structure, and loops are generally stronger than trees. But you might notice that there's a problem with making a triangle out of the double racks we have so far. We have double racks on 2 layers, a lower layer and an upper layer, and the sticks connect together at crossings where we switch from one level to the other. But a triangle has 3 sides, which is odd, so you cannot alternate your way around it. My solution for this design was to have a secret 4th corner to the triangle in the middle of this edge. Here's where it switches between the lower and upper layers. This works, but there's a pretty big downside. It can only collapse this far, because this rack runs into this one. The problem is that we've got sticks at different angles occupying the same layer. Different racks stay out of each other's way much better when they point in the same direction if they happen to be in the same layer. So we really want 3 different layers for the 3 different directions of the triangle. I was stuck for a while trying to figure out how to make 3 layers work. With the 2-layer design, we have a bunch of double racks on each layer, and the double racks around a gear are rigidly connected together through the axle of that gear. Let's suppose that we want the 3 layers to have equal angles between them, so let's rotate the upper layer from 90 degrees to 60 degrees so they can all be at 60 degrees to each other. Next, let's move the 2 layers apart, giving us room to put in a 3rd layer in the middle. Now the problem is, how is that 3rd layer supposed to stay out of the way of the gear? We could have the gear cut the middle double rack into 2 pieces, which we would need to connect together with the double racks on the other 2 layers around the outside because we no longer have access to the inside. But this isn't so easy because the other double racks on the 3 layers take up a lot of space. The solution was to realize that instead of the gear cutting the double rack apart, we can have the double rack cut the gear apart, and this doesn't really cause any problems. That's what's happening in this design. There are 2 gears either side of the middle green layer. If we move the green layer, it rotates the gears, which moves the outer red and blue layers. So the top half with the green layer and the red layer acts exactly like the 2-layer version we had from before, and the bottom half with the green layer and the blue layer also acts exactly the same as the 2-layer version we had from before. Instead, if we move, say, the red layer, the force transfers through the upper gear to move the green layer, which moves the lower gear, which moves the blue layer. So the gear train is a little bit longer, but the construction is simple and robust. The design here is probably the most natural 3-layer pattern, a grid made from equilateral triangles. It's very satisfying to move this design. You can grab any 2 points and push or pull them, and it moves smoothly. On the square grid, it can jam a bit if you're trying to push together points that are diagonal from each other. The mechanism is much happier when you push along a stick so that the gears get rotating, which makes everything else work. The triangular grid has more sticks going in more directions, so we don't get the diagonal problem so much. Here's a 4-layer design I tried based on a tiling of the plane made from octagons and squares. This one doesn't have any long straight sticks at all, so it needs a bit of jiggling to get the structure to expand or contract. It's definitely not as fluid as the grids. You might be wondering why the chunk of triangular grid I made is in this bow tie shape. I originally made just this hexagon, which works pretty well, but there's a sticking point that would sometimes come up. The issue is that even though the different layers are supposed to be out of each other's way, flexing of the design can make them crash. This could be fixed by moving the layers apart a bit more, or by using less flexible materials, but even better is to extend the pattern so that the crashing sticks meet at a proper junction with a gear. Then they're held apart for the whole motion. I did this for the places where green crosses red and blue, and there's no need to extend the pattern where red crosses blue because those outer layers are so far apart from each other anyway. Alright, let's return to the triangle I started with. Again, it can only get this small because the racks pointing in different directions share a layer and crash into each other. Here's the improved 3-layer version. Since the 3 different directions of racks are on 3 different layers, there's no premature crashing, so this triangle can collapse all the way down to here. Here's another copy of the same triangle. You can fit the collapsed shape almost entirely inside the expanded shape. I think this is one of the more interesting designs, and it doesn't require a crazy amount of printing, so if you'd like to make one of these yourself, I've put a link to the files in the description. The side lengths are in the proportion 3 to 4 to 5, so we get a right angle triangle since 3 squared plus 4 squared equals 5 squared. This right angle corner has the same parts as for the grid designs. The other corners have special gears because the angles aren't as nice. When all the sticks are collapsed down, we want the gear to be in the same place relative to the teeth of the racks. So if you imagine rotating this stick around to make this side of the triangle, you'd need to rotate the gear by this angle, which it turns out is arctan of 3/4. Or rather, you'd rotate half of the gear by that amount, which is what I did. There's a similar thing going on at the other acute angle, and this would also happen at the right angle corner, except that the gears I'm using have 12 teeth, so rotating by 90 degrees doesn't change the shape. Why did I make this particular triangle with edges in that ratio 3 to 4 to 5? Well, in order to scale the whole triangle up, each edge has to scale in proportion to its length. The easiest way to do that is to have the longer, and so faster growing sticks, just have proportionally more racks and gears along them. But with a bit more effort, we can make pretty much any shape we want. Here's an expanding 45-45-90 triangle. The hypotenuse has to be square root of 2 longer than the other sides, and it also has to grow faster by a factor of square root of 2 again. What I did here is keep the number of racks the same, 3 on this side just like the other two, and I just scaled all of the racks up by the square root of 2. Again, the gears at the ends of the hypotenuse are non-standard. Not only do we have to scale up halfway along the gear, but we also have to rotate by 45 degrees. Okay, so that's expanding racks so far. What other shapes or tessellations would be good to make with the system? And can you think of any applications for this expanding system beyond making big models of Pythagorean triangles that collapse down to fit in my luggage? Alright, that's it for now. Thanks for watching.
طبعا مثل ما انتم شايفين النادي مفتوح 24 ساعة، يعني يمديك تتمرن حديد، يمديك تتمرن جري، يمديك